Hey CW Bio, Mr. Kennedy here with part 2 of your lecture video series on Chapter 5, Population Ecology. In this portion, we're going to start talking about human populations. Humans are governed by a lot of the same rules that, plants and animals are. But rather than just focus on the impact of those rules, let's look at how human populations are even studied. So we're going to start by looking at census data. In the United States, a census is taken every 10 years, and it's one of the most useful pieces of data for helping us track the rate at which each country, each county, each state, no matter how you slice it, how that population is growing or declining. Like, this is stuff we need to know. We need to know where we need to build roads, where we need to build police and fire stations, where we need to build schools. We need to know if our population is growing so fast that we got to make adjustments in agriculture to feed people. These are all things that we get from our census data. The figures that we collect from our census data basically form the basis of an area of science called demography. This is the study of human population size, density, and distribution, movement, its births, and its death rates. When you think about all of these factors regarding human population, well, human population growth is a little different because than what we see in like lower life forms, because humans have the ability to change their environment. When we first started talking about limiting factors, food, water, space to live, all that kind of stuff, the natural tendency is to just apply that to everybody. But, if you think about people, we actually are very good at conquering the environment as opposed to coexisting with it. And if there's a food shortage, well, hey, no problem. We got the technology to go plant more or to genetically modify crops to increase production. It allows us to kind of cheat at nature's game of exponential growth and limiting factors. People live longer and are able to produce offspring that live long enough to produce offspring, and hence our population continues to grow as long as we can feed people and provide modern medicine and things of that sort to help people along the way. Now, how do we calculate growth rate? Well, it's pretty straightforward, pretty simple. There are a number of factors that determine your growth rate, but if we just try to keep things simple, it's births, deaths, immigration, and emigration. So if we lay it out this way, obviously births are going to add to your population and deaths will subtract. Do you know the difference between immigration with an I and emigration with an E? I think of it this way. The immigration with an I stands for in. I for in. So if you are immigrating, you're going in to a population. The E for emigration stands for exit. So you're leaving. So births and immigration with an I add to your population, while deaths and emigration with an E subtract. Your birth rate is the number of live births per 1,000 population in a given year. So if I said the birth rate was 5, then that would mean you have 5 live births per 1,000 individuals in your population, which doesn't sound like much until you start multiplying out the size of the population, right? If you had only 1,000 people living in an area, then yeah, you'd have 5 babies for those 1,000 people. Okay, well, if you had 10,000 people living in an area, now you got 50 babies. Do you see what's happening? If you had 100,000, now you got 500 babies. The, multiples go on and on and on. Death rate is the number of deaths per 1,000 in a population in a given year. Works the same as birth rate, but we're subtracting. Movement of individuals into the population is immigration, as I said, and out of a population is emigration. Okay, birth minus death rate equals your population growth, or PGR, right? And don't forget the immigration and emigration. If the birth rate of the population equals the death rate, then the population's growth is 0. If the PGR, population growth rate, is above 0, then more new individuals are entering the population than are leaving. A PGR can also be less than 0, and guess what that means? your population is declining in numbers. Next thing we want to consider is a population's doubling time. The doubling time is the time needed for a population to do just that, double in size. Okay? There are lots of ways that we can calculate it. Probably the easiest thing is to first figure out what your growth rate is, and then you use a simple formula called the doubling time formula, where you just divide 70 by the growth rate, and that'll give you a value. Now, the idea here is the smaller your doubling time value, the faster your population is growing. So if I had a doubling time of 10, what that literally means is it's only going to take 10 years for my population to grow from whatever it is today to twice that size. If we think about humans on this earth, right now there's about 7 billion people on this planet. So this is not a true number, but just an example. If the world's doubling time was 10, then that means 10 years from now, there wouldn't be 7 billion people on Earth, there'd be 14, right? That's a lot of folks, but that's how doubling time works. So doubling time can be calculated for the world, it can be calculated for a country, small region, or even a city. And at the end of the day, it helps us understand all those things that have started us off with, like what do we need to build schools and roads and do for agriculture, okay? Now, one of the last things that we got to talk about is a population's age structure. The age structure of population is really important because, well, it maps out those individuals that are reproductively capable in a population versus those that are not, and will help us then understand, again, how fast our population is growing. So I've got 3 graphs here, one illustrating stable growth, one illustrating rapid growth, and one illustrating slow growth. And if you look at them, they separate males from females in 2 different colors, and then they separate our individuals by age group. So the idea in stable growth, we'll start with that one. So you look closely, you can see that there is a group of reproductively capable individuals that sit right about from the age of 20 all the way up to about the age of 49, okay? And as you look at the thickness of this graph, okay, you can see that the individuals who are reproductively capable just go straight down to the babies, which basically means these reproductively capable individuals are having just enough offspring to replace themselves and no more. So, your birth rate in this case might be 2, which basically means that you're having like no more than 2 children per couple, which means as that couple grows old and dies, you have 2 children to replace those 2 people that died. So your net population growth is 0. In rapid growth, look what's happening here. Here's your reproductively capable group, and look at all the offspring that they're having, okay? By having so many offspring, like they're going to move up to the next level and potentially produce offspring of their own. This is a population that stands to grow very, very fast. A downside to rapid growth is the top end. Look at, people don't live very long, and that's probably why this population has a rapid growth pattern, right? So you're having lots of children to guarantee that very few of the people in the area can actually make it to their elderly years. In slow growth, here's our reproductively capable people again, and you can see that they're having just about the same number of offspring that there are of them, with a little bit of an increase. So we've got this indentation here that is offset by a bulge down here where the offspring are. So that's kind of like saying that, well, you're going to have a birth rate instead of being 2, which would kind of, be canceled out by death rate later on. Maybe it's 2.1 or 2.2. So there's this tiny fraction of extra. That doesn't mean that every couple that's reproductively capable is having like 3 or more kids, but at least some of them are. So your population will grow slowly. In terms of where we see these kinds of things around the world, well, a slow growth demographic map is pretty much what we see here in the United States. Rapid growth is what we see in developing countries where there's not much in the way of healthcare or anything like that to take care of the people in their elderly years. And stable growth is where we, find in places in Europe where growth has basically flatlined. Okay, so this is a demographic map that we use to track population growth of people. All right, so last few things and then we'll be all done. Ecology and growth. So the needs of populations differ greatly throughout the world. Sometimes a population grows more rapidly than the available resources can handle. It happens, okay? Resources that are needed for life, such as food and water, can become scarce or contaminated. And if this happens, well, the amount of waste produced by a population can become difficult to dispose of properly and can lead to stress on resources, contribute to the spread of disease, or affect the stability of human populations both now and in years to come. So that's it, ladies and gents. You've gotten everything there is to know about population ecology for lower life forms and for people, basic demography. I'm Mr. Kennedy, and I will see you next time.